When I started as a graduate student, I think a lot of these things start that way. There was this terrifyingly brilliant guy from postdoc in math who would come to the theory talks and ask all these very insightful questions. And then within a year, he was a terrifyingly brilliant postdoc in computer science. And now he is a terrifyingly brilliant professor in computer science here in machine learning. And he's here to tell us we're doing it wrong. So with that, Shai, take it away.
Yeah. Okay, thank you very much. Yeah, so this is kind of a very personal style of talk. I'm being controversial and I'm being negative as always. And this is kind of a preaching that I've been doing about clustering. What I'm claiming is that the world is doing clustering wrong, both the theoreticians and the practitioners, and I will try to convince you of that, or at least in what sense it's being done wrong. So let me first start. I like to start almost all my talks about machine learning with this citation from Herbert Simon, and he said that the purpose of science is to find meaningful simplicity in the midst of disorderly complexity. This is a wonderful description of what are we trying to do in science. The world is very complex, and we're trying to figure out some meaning there, but I think that this could serve as a great definition also for clustering. So you have a large data set in high dimension, tons of points. You cannot visualize it. You try to make some sense of it. Clustering is one of the first tools that you apply. It gives some meaningful structure to your data. So this we could take it as a definition of clustering, and it's really being applied all over the place. I mean, in social sciences, you have community detection. You're trying to cluster groups over Facebook. In biology, people are clustering proteins and clustering genes and clustering species. In astronomy, you're clustering stars. In computer science, people are clustering faults and clustering attacks and clustering whatever. And so we all apply clustering to gain some first understanding of the structure of large and complex data sets. However, I claim that there exists distressingly little understanding of clustering. And I will try to explain to you what is lacking, what is so distressingly lacking in our understanding of clustering. So when I'm saying understanding of clustering, I don't mean understanding of a particular algorithm. So you have tens, if not hundreds, of papers every year that analyze a specific clustering algorithm. They take k-means and they beat it to death. They take EM and run experiments over and over all kinds of data sets. But that's analyzing a specific algorithm, not the task that this algorithm is trying to solve. And the same thing, there is a lot of work on optimizing some cost function. So you say, OK, if what I want is to optimize the k-means cost, here I can do all kind of optimization and randomization, and the whole OR department can work on it. But you don't ask yourself, why do I need k-means? What am I using it for? Is this the right tool for me? So again, I mean, I'm searching for analysis or understanding of clustering and not any specific algorithm or specific cost function. And similarly, there's a lot of work starting with generative model. If your data was generated by a mixture of Gaussians, we can try and recover those Gaussians. But we are doing clustering in many areas in which we have no reason to assume that we know how the data was generated. So what we are lacking is something that is not specific to one of those narrow views of clustering. So here is a very good example. And I think David is just living in time because I'm attacking Stanford. So this is taken from the Stanford CS 229 syllabus, and this is a course by John Ducci. It's a great course. He's a great guy. And here is two items from the syllabus. And I want to contrast what they teach you about learning theory and what they teach you about unsupervised learning, which is clustering. So about learning theory, they talk you about bias, variance, trade-off. That's a very important principle in statistics. They told you about Cherniff bounds and Hofding bounds and visit dimension. There is a lot of theory, deep mathematical understanding. When it comes to unsupervised learning or clustering, what do you get? Clustering k-means, EM, factor analysis, PCA, ICA. This is a laundry list. There is no insight, there is no theory, there is no depth. And it's not just the Stanford course. You take any machine learning book, you look at what they have on other areas of machine learning, like supervised learning. There is a lot of theory and understanding. You come to clustering, you just get a laundry list of algorithms. And that's it. So we really are in a lack of principled understanding of what clustering is, what are we aiming for. And, okay, so what am I going, oh, did I press the wrong thing?
Stop by accident.
Right. Okay. Yeah, so I'm going to talk about two different topics. If I have enough time, I definitely will talk about the first one. So the first one is model selection. How would you choose the best clustering algorithm given a task? So you have some task, you want to cluster your customers for some kind of giving them all kind of bargains. Which algorithm will you choose? What is a good algorithm for a given task? The other question that I'm going to talk about is the computational complexity of clustering. There is a big discrepancy here between theory and practice. Everything you try to do in clustering, when you analyze it theoretically, it is NP hard. In practice, it's run of the mall all the time people doing. Okay, so I will talk about these two topics, and let me start with the first one. Given a clustering task, how should a suitable clustering paradigm be chosen? So you want to do some clustering. You are a biologist. You are an astronomer. What will you use? And why is it an important question? Why is it more important in clustering? Because given any concrete clustering task, you need to choose a clustering algorithm. And unlike common computational tasks, the different choices may lead to significantly different outcomes. If you want to do sorting, and you choose one sorting algorithm over another, it may run a little bit slower. But at the end, you will get the same sorting. That's the sorting of elements. But if you pick two different clustering algorithms, you may end up with completely different outcomes. Here is the simplest example. Look at this cloud. If I want to cluster this set of points, if I pick k-means, two means, I will get the clustering into red and green. If I pick single linkage, I will get this clustering. There are two different partitions are as different as possible. And it just came out of the choice of my algorithm. Now, of course, if I'm in dimension 2 and everything looks like nice clouds, then I can say, oh, this guy makes sense, this guy doesn't make sense. But if you're in dimension 300 and you have 2 million points, you cannot even visualize what you get. You picked an algorithm, who knows why, you got an answer, you don't have any clue that if you pick a different algorithm, you will get a completely contradictory answer. So here, the issue of picking the correct or the suitable clustering algorithm for your task is much more important than in many other computational tasks that we carry out. It really has a huge impact on the outcome. Okay, so maybe we should go to the definition. Start with the definition. Want to understand what is clustering, go to the definition. So the common definition is that what is clustering? You have a data set. You want to partition it in such a way that similar points will reside in the same cluster, and these similar points will be separated into different clusters. That's what you are trying to get. So let's work with this definition. The problem is that these two requirements can often be contradictory. And this definition doesn't tell us how to handle contradiction. What do we do when these two requirements cannot live together? So here is a very simple example, a very simple impossibility result for clustering. I will show you that you cannot satisfy both of those requirements simultaneously. So pick any, assume that I get data and I have a distance over the data, and I'll pick some value alpha, such that every 2 points which are closer than alpha, it will be a small number, I will consider them to be similar. And I will pick some big beta, such that every point which are more than beta apart, I will consider them dissimilar. And now I want to cluster similar points together and separate dissimilar points. Can I do it? And the answer is no. Why no? Because look at this data set, right? If every 2 points here are close enough that I consider them similar and I want them to be in the same cluster, then I'll end up putting all of this line in the same cluster. But if I did that, then this guy and this guy, which are far and should have been separated, they ended up in the same cluster. So what I'm saying is the requirement, every 2 similar points should be together, and every 2 dissimilar points should be separated. They are contradictory. I mean, if you want to phrase it mathematically, clustering is an equivalence relation, partitioning is an equivalence relation, similarity, and therefore it's transitive. Similarity is not transitive. A can be similar to B, B to C, C to D, but A will not be similar to D. So we have an inherent dilemma here. And this is not the only dilemma that is troubling us in clustering. So we can think of clustering as somehow we have a simplex of requirements. We want to join together similar points. We want to separate dissimilar points. We may want the clusters to be of roughly similar size, not to have 99% of the points in one cluster and 1% of the points distributed over 100 other clusters. We may want robustness to outliers. There are lots of requirements, and we cannot satisfy, for any 2 of them, there may be a contradiction between them. So when you pick a clustering algorithm, you have a clustering task, you have to understand what are your priorities among those requirements and pick an algorithm accordingly. And we don't have tools for doing it, and people are not doing it this way. I mean, they don't have tools is my criticism of the theoretician. People are not doing it this way is my criticism of the practitioners. But I will get to it more concretely. So let us look at different clustering algorithms to see that they really have different focus, different priorities. So single linkage, I guess many of you know what single linkage is. Single linkage is the simplest clustering algorithm. You look at your data, you find the closest 2 points, you put them together. And then you keep going. You have clusters. Every time you want to keep merging, you look at 2 clusters, you define their distance as the distance of the closest points, and you each time merge the closest 2 clusters. So you build a clustering tree, and you have to decide where to cut it. If you do the clustering this way, each time you merge the closest points, then what you really emphasize is similar points should be in the same cluster. Whenever you see 2 similar points, you put them in the same cluster. And you don't regard any other consideration, just this consideration. And that's a very common algorithm, single linkage. Another very common algorithm is max linkage. Max linkage works almost the same way, but now when I want to merge 2 clusters, I don't consider the closest point, but I consider their furthest point. So such an algorithm is also a very common clustering algorithm, but its only consideration is how to keep far points separated. So it really goes to the other extreme. And this is another common algorithm. Another common algorithm, I mean, both of them are oblivious to cluster sizes. In both of them, you can end up with one cluster having the vast majority of the points and all the other points floating around as singletons. If you want to introduce the consideration of cluster balance, think of, for example, of k-means. K-means is another very common clustering algorithm. In k-means, if you look at it carefully, you realize that you also care about the size of the clusters. K-means can cut a dense cloud of points just to make sure that you won't have one big cluster and the other small. So what I'm saying, different clustering algorithm, when I showed you this simplex of different conflicting considerations, it's not just abstract. It's really embodied in different clustering algorithms. What about, do we really need all those considerations? Let's look at clustering tasks. So that's another clustering algorithm does the different priorities. So let's look at clustering tasks. So one of the tasks I've been kind of talking about a lot with eHub is data deduplication. The database group here, we are experts in data cleaning. And one of the things you do, you have a record of all kind of patients that came from cold clinics, and you have duplicates. And you want to merge the duplicates together. If you have a very big data set, say I have a Census Canada data set, and maybe I have replicas of the same person appearing twice in 2 records, I cannot do it manually. I want a clustering algorithm that will do it for me. The clustering algorithm should find duplicates, or almost duplicates. Here, the emphasis should be on not putting together these similar points. If you want to cluster for data duplication, and I have one record where the patient is 86 years old, and I have another record of a patient that looks quite connected in a chain of points, but he is 2 years old, I will not claim that it's the same patient. So here the emphasis is not merging, not putting together these similar points. Another application of clustering is if I want to cluster people to predict a viral spread. Either a virus as a disease or a viral spread of a rumor of some trend. In this case, if I want to cluster for predicting viral spread, I want to make sure that every similar points are together. Right? If I meet someone daily and I get flu, he's likely to get the flu. And I don't worry that in my clusters of viral spread, I will have 2 people that are completely disconnected because they can get the same virus through a chain of connections. So here you see the emphasis is the opposite. Here I want to make sure similar points are together. There I wanted to make sure that these similar points are not together. And both of them didn't worry so much about cluster sizes. But if I want to cluster neighborhoods for school districts, now suddenly I have to worry about cluster sizes. I want to have one school district that will have 3,000 kids, and other school districts will have 100 kids each. So what I'm saying is that those different requirements are not just abstract. They really vary with the algorithm that you use, and they vary with the application that you use it for. So it's an important consideration. So how is it being done in practice? Now that I try to convince you that this is an important consideration, how do people pick a clustering algorithm for the purpose? And this is something when I do it with a smaller audience, less respectable than you, I can ask people, who is using clustering here? How did you pick your clustering algorithm? And the answers that I get are embarrassing. Really. How do people actually pick clustering algorithms? So this is done by the most ad hoc manner. The first answer, I guess, is easy. This is easiness of use. No need to tune parameters. That's why I picked my algorithm, because it's easy to use. Great. But is it relevant to what we need? Another is it's really downloadable software. That's a very common answer. And another one is it worked for my friend. But maybe your friend had another problem, not your. And these are answers that you get from scientists, from people who are so sophisticated otherwise. You don't get any other answer when you ask someone, how did you pick this clustering algorithm? I'm going to NIPS, to important conferences. I go to all the clustering posters. Someone tells me, they cluster patterns of use of electricity in order to find similar people. So I asked this presenter, what is the purpose of this clustering? And the answer is to satisfy the electric company. So that doesn't give me any clue. What should I do, right? And runs fast is another good answer that we get. But I can give you an algorithm that runs very fast. Put all your points in one cluster. This runs in constant time. And another claim that I see in many scientific papers, my algorithm outperforms all others. This is the same in analog as saying this medication is the best, regardless of what your disease is. It cannot be best because every purpose needs something different. There can be no universally best clustering algorithm. Oh, here is an algorithm that can be implemented in linear time. Okay, this is, you're sick, take this pill, it's only 99 cents. It's the same thing. It costs you a little. Take this. And again, I mean, I'm not making fun of stupid people. I mean, here, I mean, this is what I'm reviewing tens of clustering papers every year for the best conferences. How do people show that the algorithms work well? They check against inherent structure of the data. Inherent structure of the data is very nice if your data is two-dimensional and looks like a set of balloons which are well separated. Inherent structure of the data is what you're trying to discover. You don't know it when you have thousands of dimensions. Another answer that I get, experimental evidence. Every paper in clustering has experimental evidence. I can bet you that for every 2 reasonable clustering algorithms that you give me 2 algorithms, tell me which one you want to win, and I will give you a data set on which this one does better than the other. It is completely meaningless. And okay, so this is just to show you that I'm really talking about smart people. This is an article from Science last fall. And it's just, the reason it's from a year ago is that I keep updating this slide. Every time there is another article like this in Science or Nature, or you pick it. And this is by a guy, I mean, that I really like, and Jure Lashkovitz from, right? And see what they're writing. These frameworks provide mathematical guarantee of the optimality of the obtained clusters. What is this optimality? How can you give me mathematical guarantees of optimality when we don't know what we're doing? I mean, you're invited to look at those papers and see that this is exactly the fallacy they're falling into. They're claiming my medicine is best regardless of your disease. Okay, so what should we do? Let me try to be positive, which is not my nature, but I can make it try. So to turn clustering into something which is well-defined, we need to add some prior domain knowledge. We need to, when we want to match an algorithm to an application, we need to understand our application. We need to introduce domain knowledge. And the question is, how can we do it? So how can we translate domain knowledge into a tool that is useful for someone that picks the algorithm, someone that knows here is a library of clustering algorithms, and I can direct you what will be good for you. So one direction that I tried for a few years with some students, with Rita Ackerman, for example, is an axiomatic approach. So the axiomatic approach is we try to formulate properties of clustering. Every clustering algorithm will have properties like we did before. And similarly, we will have properties of your application, and it will try to match. I will talk a little bit more about it in a second. Another approach is the interactive approach. So the interactive approach is I start clustering and I interact with my user. And I ask them, are you happy? Do you have any suggestion to change something? And I'll show you what we can do in that direction as well. So rather than doing things abstractly, we're just doing it on the run, very down to earth, communicating with the user. So this is kind of an ideal picture that we were hoping to get with the axiomatic approach. So here what I have is different properties that I would like my clustering in the columns, different properties that I may like my clustering algorithm to satisfy. Say it should be scale invariant. If I multiply all distances by 7, the partitioning should be the same. Say I want to have some kind of richness, that I can get many types of clusters. Or I want to have some consistency. So here are all kinds of properties that I may want my output clustering to satisfy. And here I have a set of clustering algorithms, like I showed you in the second slide. And I can now mark in my table for every clustering algorithm which of the properties it satisfies. As we already know, every algorithm will fail some of the properties because they may be contradictory. So now the hope is that my user will come and say, these are the properties that I need. Then we will search in the table and see, do I have for you a clustering algorithm that has pluses in all the places that you wanted? So we tried this approach. the main challenge that we couldn't really overcome was how to come up with properties that make sense to the customer. I mean, how to develop a language that it will bridge between the algorithmic design and the practical application. You cannot come to a doctor and say, you know, I want a measure of similarity between patients that will be positive semi-definite. We are losing the connection with them. So we could, I mean, this approach was useful in the sense that it got us a big chunk of papers on our CVs, but I'm kind of feeling that it's too difficult. The challenge is develop a language on which you can communicate with your user. So we switched to a different approach, the interactive approach. So what is the interactive approach? We are asking the user all kind of concrete questions or interact with the user about their data. So we can ask them, do you have points that you know that should be together? Not if he knows that it should be together, he could put them there himself. But I'm trying to learn through this something about the requirements of my user. So there could be must link and can't link answers or questions that I will ask my user. Another option is to have merge split. So I'm giving my user a candidate clustering, and I ask them, do you see one of the clusters here that you would like to split that should not be together? Do you see any two clusters there that you think they should be merged? That's another type of interaction. Another type of interaction that's in a paper that we had 2 years ago with Hassan is sample clustering. Why do the user come to an algorithm for clustering? Because the data is too big usually. So I will take a small sample of the data and ask the user to cluster it manually. And I will try to learn from the way the user manually clustered this small data set, how should I cluster the big data set? So we have some work along this direction. Each of those has some advantages, but of course doesn't solve all of the problems. In some scenarios, the user cannot give me such answers. Everything is kind of a limited patch. It's not a definite, complete answer. So I just want to mention one positive work. This is work from NIPS last year with my student Hassan and Shrinu. And we considered a system where we called it semi-supervised active clustering. So the algorithm each time shows 2 points to the user and asks the user, should they be together or not? In some cases, like the data deduplication, the user can answer it. If I show you the records of 2 patients and I ask you, is it records of the same patient or not, usually my user will be able to answer it. So I have such interaction with the user, and I use it to do my clustering. And we show that few such queries can turn an NP-hard clustering problem into solvable one in linear time. So I'm looking here at a different aspect, not only that it gives me clues about what the user wants, but it also gives me a huge speed up in the run of my clustering algorithm. So I introduce here another consideration with computational complexity. And another consideration is it will only work on data which is clusterable. On these 2 topics, I will talk a little bit more later. But we usually, what we want to do is clustering only when data is clusterable. If my data is just a cloud without any structure, then we don't really need to cluster it or it will be meaningless. Okay, so let me just talk about the concrete results here, and then I will move to the computational second part of the talk. So here we have a notion of niceness or clusterability of data. What do I mean by my data has inherent structure? So I will be looking at the task that the data has inherent structure, and now how can we find this inherent structure? So here we have a parameter gamma, and we have a data set X with some notion of distance. And we say this is gamma margin nice if we have this situation that for every, these are the mu i's are the cluster centers. For every point, the point for every point x, if x in the cluster that belongs to mu I, and I'll take their distance, then even when I multiply it by gamma, I will still be less than the distance of any point that does not belong to this cluster from the same center. So this is kind of saying around every cluster, I don't tell you anything about the shape of the cluster, but around every cluster there is some kind of a margin. This tells me the data is very nice. Maybe it is now will be easy to cluster it. So with this niceness, we can show that there is a phase transition. Although it looks like a strong requirement, if gamma is greater than 2, if every point outside my cluster is twice as far from my center than any point in the cluster, then it's very easy to cluster. Then we can do it fast. But on the other hand, the surprise thing that if gamma is less than 2, there's a sharp jump in the complexity. And once the margin is just goes over this threshold of 2, I go from an easy problem to an NP-hard problem. So I have here a notion of clusterability, which says around every cluster it is some kind of clean margin. And although it looks like it will solve all my problems, it seems that we show that if the margin is really big, things become easy. But if the margin is less than 2, factor of 2, the problem is still NP-hard. So now we are looking at data. We are asking ourselves, how can we solve this kind of problem? And what we show is that we make very few queries. We make queries to the user that we give them a pair of points and ask them, should they be together or not? And we only ask logarithmic number of queries. And we turn this task to be, we can run it in linear time. You see, linear, n is the number of points, k is the number of clusters. We can run it in linear time whenever gamma is bigger than 1. So let us recap what I'm doing here. I have a notion of clusterability. Clusterability is some kind of margin around my clusters. If the margin is less than 2, then it's NP-hard. But if the margin is bigger than 1, then with few queries, my problem becomes very easy. Although without the queries, it was NP-hard. So we get this situation that for gamma between 1 and 2, when the clusterability requirement is mild, it's not negligible, but it's not strong, then the task is NP-hard without queries, but with these simple queries, logarithmic number of queries turns this NP-hard task in the same domain to a task that can be doable in linear time. So we have here a situation in which the communication with the user, if the user could answer those queries, not only gave me clue about what the user is searching for, but it also helped me cut dramatically the running time of my algorithm. And we get such guarantees. So with this, I finished the first part. The main message was we cannot do clustering blindly. We need to domain knowledge in order to pick a clustering algorithm. And one way of getting domain knowledge is interacting with the user, and this can be helpful in other respects as well. Now, yes?
What happens with gammas exactly?
Yeah, and I think I have a small point there that I don't know the answer to. I mean, last time I gave this talk in Berkeley, and my student Shrino was there, and someone asked this question, and I thought he must know. And I embarrassed my student for no reason, so it's better to embarrass myself, yeah. But it's still a very unusual phenomena that you have such a threshold that above it, it's easy, below it, it's NP-hard. And then once we introduce our queries, it becomes easy all the way to 1. OK, so let me switch to my second topic of understanding clustering. And this is the question of computational complexity of clustering. So is it the case that clustering is hard only when it doesn't matter? I mean, clustering is known to be NP-hard. Many clustering tasks are NP-hard. So two guys friends of mine from the Hebrew University, Nati Lineal and Amit Danieli, they coined this thesis. Maybe clustering is hard only when it doesn't matter. So the reason is that worst case complexity, I mean, it takes us into a slightly different discussion. When we do computation, when we do theory of computer science, we usually do worst case complexity. I mean, I don't know who are the complexity people here in the crowd. And Jonathan, whatever. You do worst case complexity. That's what you know how to analyze. That's what we understand. That's where we have beautiful results and beautiful big open problems. However, worst case complexity is focusing on hard and maybe very, very rare instances. A problem can be NP hard, and the instances where you hit hardness with some algorithm can be so spread out that you will never see hard instances. So in some sense, the theory that we like and know so well is not a good match for reality. And there are many examples like this. I think the first example is propositional satisfiability. We all know that SAT was the first problem that was shown to be NP hard. That was the work of Levin and Cook. This is the pinnacle of NP hard problems. When I was a student long time ago, you wanted to show that the problem is hard. You reduce the problem, you reduce SAT to your problem. Why is my problem hard? Because if I solve it, I can solve SAT. That's what is happening now. Now we have very strong SAT solvers. You want to show that your problem is easy. You translate it to SAT and feed it to a SAT solver. So it became like the run-of-the-mill algorithm that works wonderfully. To solve something easily, you translate it to SAT. And we still don't have the answer. I mean, worst-case complexity is very pessimistic. In reality, SAT solvers are working beautifully on tens of thousands of variables. Why? We don't know. Similarly, we have linear programming. So here we have some answers. The smooth complexity of Teng and Spielman. Neural network training. I mean, we all hear about deep neural networks and how they solve all the world problems. Theoretically, to train a neural network of depth 3 with 3 nodes in the middle, it's NP hard. Just 3 nodes, 3 nodes in the hidden layer. You have an input layer, 3 nodes in the hidden layer, 1 output layer, NP hard. So there's a huge discrepancy between theory and what is happening in practice. Now, I want to address this discrepancy for the case of, say, k-means clustering. So k-means clustering is another problem that is known to be NP hard. It's NP hard whenever the number of clusters is bigger than 2, and it's NP hard whenever the dimension in which you work is bigger than 2. So it's really an NP hard, very NP hard problem, NP hard to approximate, whatever. But we do it all the time. The question is, can we come up with a theory that will explain when is it easy? Why is practice so different than theory? So most kind of the common answer that I was trying to promote is saying maybe this hardness has to do with the structure of data that we see. Maybe in reality I don't see really hard data. So does the hardness still apply when I restrict my attention to clusterable inputs? And that is this thesis of clustering is hard only when it doesn't matter, so let's call it CH&M thesis. And recently, in the last 10 years, this has been attracting more and more research. So people were trying to really believe, I mean, people believe that maybe this is the answer. Maybe this is also the answer to the success of deep neural networks, that the data that we see is structured, is nice. Reality is much nicer than worst-case scenarios in worst-case complexity. But I will not talk here about deep learning. I'll talk about clustering. So how can we support the statement that clustering is hard only when it doesn't matter? So what we will have to do is to come up with some notions of clusterable data, such that we can convince ourselves that real data is really clusterable, and then prove that if we restrict our attention to this notion of clusterability, our algorithms can run fast. So this is the program. And what I want to do is tell you what is the state of the art along this line. And this is a very important kind of shift in theoretical computer science, which I think will spread to more and more areas. Instead of just looking at worst case, try to understand what are the regularities of naturally occurring data and show that in such cases you can do better than worst case complexity. So here are some notions of clusterability that have been proposed. I will not do a lot of it, just to give you a feeling. So one of them is perturbation robustness. You can say the data is perturbation robust if when you take your data and you perturb it a little bit and you cluster again, you end up with similar clusters. So small perturbations will not dramatically change your clustering. That's perturbation robust. We introduced it in 2009 for additive perturbation. In 2010, Bilu Lineal introduced it for multiplicative perturbations, but it's the same kind of philosophy behind it. Data is clusterable if small perturbations will not change the desired outcome. Another very different notion is the notion of epsilon separability, and here we compare. We say the data is 3 clusterable if by requiring that I'll have only 2 clusters rather than 3, the cost of clustering jumps up. You see, here if I have 3 clusters and I look at the average distance of a point from its center, it's very small. But if I just force you to do it with 2 clusters, you will have to put a center here, and suddenly the average distance of a point from its center will go up dramatically. So I can say if this is a situation, if by going from k to k plus 1, I save a lot of cost, maybe the data really has a k plus 1 structure. That's a very different approach than the perturbation robustness. Another approach is uniqueness of optimum. If I try to cluster this into 2 clusters, I have this solution and I have that solution, and both of them look similarly nice. Maybe clusterable, maybe that is indication that 2 is not the right number of clusters here. Maybe an indication to being k clusterable is that when you fix the number of clusters to k, there is a unique solution. And we can phrase it precisely. Another is center stability, saying data is clusterable if every point, when it has to choose which cluster to go to, the decision is easy. There is a center that is much closer to it than any other center. And this seems to be technical, but it is in the core of all the other results. So points are closer to if points are closer to their center by a factor more than to any other center, we say the data is clusterable. A different notion of clusterability. Okay, so what are we trying to do? We're trying to come up with notion of clusterability that will explain why things work in practice, while in theory they're NP-hard. So with all those of notions, really we can show that there is efficient clustering algorithm once the data satisfies this requirement. But if this should be an explanation of why things work in reality, what is missing here? I'm telling you, if this condition is met, the algorithm will really run fast. But I want to explain why it runs fast in reality. So what component is missing? Does reality really satisfy these kind of conditions? So let us examine this. So none of them can be efficiently verified, but the main problem is that except one notion, all of them seem to be really unrealistic requirements. Now, when I look at stock Fox JCM papers and tell them what you're doing is completely irrelevant, I need to have some hard evidence in my hand. So let me show you what do I mean by hard evidence. So for example, one of them, epsilon separateness, this paper in JCM 2012, when you check the constants, you know that when you write complexity papers, you look at asymptotics. Who bothers with the constants? But when you check the constants, you realize that in order for the efficiency to kick in, you need that every point is 200 times closer to its center than to any other center. So is it a realistic requirement that your data is such that every point is by a factor of 200 closer to its own center than to any other center? That's when you check the constants there. Another one is uniqueness of optimum. Then you can say, you can show that this factor goes down to 20 times. But it's still completely unrealistic. So I could check each of those requirements and show that in order for the efficiency to kick in, you get to domains that are not realistic to expect from real data. Now, what is the next question that the theoretician will ask here? You know, maybe it is just due to our limitations of ability to prove. Maybe it is efficient for much more realistic data, but we just don't know how to prove it. That's when I called upon my son. The Ben David here is not me, it's my son. And he could show that this is becoming hard whenever alpha is less than 2. Alpha is by how much you're closer to your own center than to any other center. So this is already an unrealistic requirement. Your data is such that every point is by a factor of 2 closer to its own center than to any other center. So what we are seeing here is that the theoretical hardness kick in even before the data becomes realistic. It can be ruled out only for very, very theoretical constructs that are not realistic at all. Yes? What? Yeah, this is new. Yeah, this is a good question. There are different constants for the Euclidean distance or for arbitrary metrics. Right. Okay, so this center stability is still unrealistic and too nice. So what is the bottom line? The bottom line is that all of those structures, they all detect, all of those notions of clusterability, they all detect a structure on which you can have efficient algorithms. But on the other hand, none of them is realistic, and it is for an inherent reason, not just the limitation of our ability to prove. So I feel that the current approach to define niceness in terms of separability is too restrictive. And so let me just talk about a little bit, I mean, we are nearing the end, just some alternative directions. First of all of the theoretical approaches to clustering talk about minimizing the cost. But a user, does he really care about minimizing some cost? We know that the user can never, if you gave him a solution, he can never even check if you were minimizing the cost. There's no way he can check it, because it's NP hard to check. So does the user really care about minimizing the cost, or should we come up with different constructs for what is a good clustering? That's one direction. Another direction is that should we care about the exact number of clusters? In all those algorithms, in all those constructs, mathematical constructs, we fix the number of clusters and try to optimize. But if you think of the task of deduplication of records, do you know in advance how many clusters you will get? You don't know. And it's not that you will be less satisfied if I gave you many clusters than if I gave you few clusters. You want to get the correct answer, and you don't know what the number of clusters is, and you don't care about it so much. So maybe that's another direction. Can we come up with precise notion of success that are not tied to a fixed number of clusters? So there are lots of open questions here, or lots of interesting directions for further research. And we don't know how to solve it. Another open problem, which is very important, can similar approaches can be applied to other tasks that are being run in practice, but in theory are NP hard? Can we get some insight into the SAT problem through this approach? I tried it. I had a PhD student that got very excited by this story about the gap between versus complexity and reality. And she worked for half a year on this problem. And then I realized that it's either we keep digging on this problem, or I want her to get a PhD at the end. And I picked the other alternative, and we don't know a good answer for the SAT problem. And it's a very important question. Okay, and will this analysis lead to new useful algorithms? Thank you very much.
Are there any questions for Shai?
Yes.
Sorry, so, and I'm probably missing something important here, but you kept talking about optimal clusters, and I don't even know what that means.
Right. So I had two parts of the talk. And in the first part, I told you, you don't know what you are trying to optimize. In the second part, I was trying to look at where the theory is nowadays.
Right.
And the theory, I mean, there is a realm of clustering where you define a cost function, and you're trying to optimize to find a solution that minimizes this cost.
I see, so the different algorithms are given the same cost function, and if they
No, no,
minimize
no.
that cost,
Different algorithms have different cost functions.
so they get different clusters.
But all of them are NP hard to approximate. Yeah,
How
and
can they be optimal then, if they're all different?
No, no, no. They're not optimal in the sense of the user.
Yeah.
They're mathematically optimal. You say, here is my cost. If my user believes that this is the cost, which is never the case,
Got it.
then I'll run my algorithm and try to approximate
Got
it.
it, okay.
But you go to Stock, Fox, Soda, you have tons of paper on working on a specific cost, K-center, K-means, and beating the hell out of it.
Okay, thanks.
And didn't you also point out that, you know, this, using the word algorithm here is incorrect, because at least my notion of algorithm is you can check that it did it right, and there's no check of it did it right. I mean, it seems to me that clustering is an abstraction of a whole family of algorithms. So
Right. No, clustering is an abstraction for a whole family of algorithms, and we don't know how to check that it did it right. But it's an algorithm in the sense
you have
that
to map it down to a point where you can say it did it right, don't you?
a question that would be a nice goal, but I think it's not the most important one. I mean, it's an algorithm in the sense that when EAB comes to me with his hammer and says, we are doing data cleaning and we want to find the duplications, give me a program that does it for me. In that sense, it's an algorithm. But his only way of verifying whether the results are good or not is to go back to the customer and see if the customer is willing to pay, or they tell him, run it again. So it's algorithmic in the sense.
The definition of an algorithm is you can verify the results of it. If you can't verify the results, then as you're saying, it could do anything, right?
Right. But you see, we are. Yeah.
One cluster all the time.
I know,
I
but
mean, because the definition is basically throw things in a bunch of different buckets, and I don't care how many you have. So anything can do anything.
anything can do anything. My main argument is that it's really a practical thing. People are doing it all the time. They feel that they are gaining something out of it. They're investing tons of money into doing it.
I agree.
And I'm trying to understand, how should they do it? That's...
So about the interactive, let's not call it algorithm, the interactive method.
Right.
So if you, yesterday we learned that we should not trust the user, right? We should not trust the user. If you give the input with some random things but some cluster, will that be equivalent to your method? So the input in your method is some set of things, right?
Right. Set of,
And you
say,
go
vectors.
You go back to, among those, you pick something and you go and ask the user.
Right.
Let's take the user out of the picture. If your input, I give you some clusters and a big other set.
Right.
Will
I
be
mean,
equivalent?
one approach is say, oh, I'm hiding some real clusters in my data and ask you, can you recover the clusters that I hid here? And that's an approach that's being worked theoretically. But for a user, it's more important to me to figure out what do they have in mind. I mean,
No. I'm thinking, so I don't want to use the user, okay?
I
So I want
see.
to change the input. This is equivalent. If I give you the cluster to begin with, plus some other
Right.
big set, is this equivalent? Do I have the same answer?
yeah. I mean, this is an approach that people use. We can do lots of theory about it. We can say, I mean, we have results that saying if you give me clusters that are well separated, and then I add noise, so much noise, my algorithm I can prove to do that will recover the original clusters. But we do have results of that nature, but I'm saying in reality, there is another aspect, and the other aspect is that for a particular application, I don't even know if there are clean clusters there, but the user needs some partitioning.
So it seems the answer is yes.
Are there any other questions? In that case, I'd like to thank Shai for a great talk. Give him a local gift. And I wanted to point something out. Shai is not a David R. Cheriton Research Fellow. He's actually a Ross and Muriel Cheriton Research Fellow. So this was from the previous endowment before the original endowment, which we give out every 3 years. So Shai is most recent to that. So thank you very much, and thank you to all the speakers in the session. But hold on, we now have prizes.
Can you bring up the other topic?
Okay, so now we have to project it.
Make it big.
Make it big. How do we make it big? And I know how to use the PowerPoint.
Oh, okay. Yay, there we go. Awesome. How do I turn the mic on? Does that work? There we go. Oh, I just need one mic, right? Yeah.
I have two
Good.
mics is twice as good.
Stereo. All right, so we've come to the end of our 2-day Cheriton Symposium. As many of you saw, we had the lovely posters out front. I've just been told the posters have been taken down by the school, and you can get them back next week. Next week. So you'll get them back next week after they've been checked for bugs or something. I don't know. Okay, so if you presented a poster, thank you. We had many great posters. Thanks so much to all the poster presenters. We had 29 people presenting posters, which was great. And of course, each poster was judged by a couple of the judges, so thanks to the judges. Yay, judges. All right, so on to the winners. So we have some runners-up who get $200 prize. It's not a big, oversized novelty check, unfortunately, and neither am I doling out cash money. It just magically appears in your Quest account somehow, kind of anticlimactically. Okay, so the runners-up are Akshay Ramachandran for Paulson problem and operator scaling. Yay. And Ivana Kajic for biologically plausible neural network model of semantic memory search. Yay. Okay, and the winner is a $300 prize, also magically appearing in your, that is Corwin Sinnamon for a faster data structure for distributive lattices. Yay. So all these winners, when the judges judged your posters, each of these winners had at least one judge who indicated on their scoring sheet that they literally blew them away. Maybe not literally. They blew them away with the quality of the poster, quality of the research, and the quality of the presentation and answering questions. So these were the 3 categories by which the posters were judged. And for each of these 3 winners, the students did an absolutely fantastic job. So let's give another hand to all the winners and all the poster presenters and all the judges. And that wraps up the session.
Not quite.
Not quite.
One more thing. I think there are some thank yous
Boom, boom, boom. Okay.
that need to happen beyond the judges and Ian and the speakers, and of course David and Fusun for coming. We should thank the people who helped organize it. Angie Hewitt, Joanne Hardy. You sent them home. And especially Diana Timmermans, please stand up. It's fantastic. We wouldn't be able to do it without you. And Justin Wan, who did a lot of the, please stand up. So thank you very much to all of you. We wouldn't be able to do it without you. Thank you to everybody else for coming, and enjoy your weekend. Thank you. Bye-bye.